So this is a pretty hefty topic here to try to do in 50 minutes, but we'll give it our best shot. I'm using these old overhead projectors because I was nervous about drowning the document camera. There's going to be hot water and soap and glycerin, and so I don't know if they're going to work, but they seem to. They got light bulbs in them and things. So I've got these. It's really funny. We pulled this out. Nolan, where are you, Nolan? Yeah, and we were like blowing the dust off of it, but it looks like it works. So we'll see what happens. One of my heroes well, I should tell you, this is a topic I studied back in the 70s and 80s for many years, and the basic problem is still unsolved. So I'll tell you what the basic problem is. But there's a book here by C.V. Boyes. If I had the document camera on, you could see it, but I don't. And it was a book for 12 and 13-year-olds, but of course this was in the 1800s, and 12 and 13-year-olds were way advanced back then. But it's a really interesting book, and I learned a lot from Charles Boyes, who became Sir Charles Boyes. He had this way about him where he said if you don't know something, there's two ways of finding out. One way is to find a resource, so somebody that knows the answer, or a textbook, or some kind of source. Back then there wasn't the internet. And he said, but the other way is you ask a question of nature, and if you ask the question properly, you might get an answer. So he, as I, were very fond of doing experiments, and I tweak things and mess around. I like experimenting as well. So before we get to soap, we have to understand a little bit about how surface tension works. Yeah, so we're going to play, I've got a picture of Charles Boyes. Boy, this is really old. There he is. Died in 1944. He was a pretty cool guy. And so I don't know if I'm going to actually follow this plan, but this was the thinking of what I would try to do today. I don't think that's all going to happen. But we'll talk about the telephone problem just so you have an idea what's underneath at least part of this. I don't know where to draw it, so I'll go over here and then we'll bring this down again. The famous problem is if you had a bunch of cities and you wanted to connect them with underground cable or whatever, shovel walks between them. The question is, what's the minimal path that you could find between n number of points? So it's pretty easy if you have 2 points, right? That's not too bad. Even 3 points is solved. In fact, we could look at 3 points. So if you had 3 points and you wanted to find the minimal linear linkage is what they often call it, which means I could certainly do this and have them all connected, and now everybody can talk to one another if it's a telephone. And let's say each of these are a unit in length, so then I've got a path of 3, but I could still have everybody talk with a path of 2. And maybe you're aware of this problem because this is the simplest of all the problems, but there are smaller paths, smaller than 2. Do you know what they are? Does anybody want to tell me what one might be? What's the thought? Yes, Anna.
Maybe you could find like the center of the triangle or the
centroid.
Yeah, and then draw.
Emanate out to there. Yeah, you could do that. So I mean, but there's all sorts of other paths. You could also draw this and draw that. And if you know your equilateral triangles, I don't know what that is. Square root of 3 over 2 and 1 plus I don't know what it is, 1.8 or something like smaller than 2. But Adam's right. You could put a point somewhere interior and you can emanate outwards. And if you pick the right point, you get down to a length that's smaller. But then when you start adding in more points, so if you have 4 points and if you have 5 points and you have 6 points, you're not fighting with the ball hanging on a string. It becomes very complicated. In fact, the computing capabilities for finding the minimal linkage, at least 10 years ago, was 29 points. Now it's higher because we have better computers. But it's a complicated problem. It's called an NP-hard problem. You know what an NP-hard problem is? So in layman's terms, it's not going to be solved in polynomial time, non-polynomial. So that means it's going to take a while. And it does take a while. So what do soap bubbles and soap film have to do? Oh, this guy really likes it. We'll find out. So I'm not going to spend as much time as I normally would because I'm fighting the clock here and I want to get to as much stuff as I can. But water is interesting, and if you've played a lot with water, then you probably know that the surface is different than the interior of the water. If you actually have to break through the surface to get down inside the water. And if you don't believe that, then just look at the water bugs that are walking along the surface in the summer, and then if you poke a hole through with your finger, they go right through. And then you hopefully pull them out again and put them back on top somewhere else. And there's lots of ways to look at this. This is a Charles Boyes thing, which I think is very cute. I don't know why, I just love his stuff. He says if you take a regular paintbrush and it looks like that, it's just got dry bristle, what are the things called? Bristles? So they're dry, and if you put the brush into water so it's underwater, what do the bristles look like? Go out, they expand. Well, I mean, as you push down, the pressure would, but I mean, if you aren't moving it and it's not in the plunge motion, if it's just sitting underwater, maybe you think it would pull together or something. Actually, if you put it underwater, it looks exactly like it did when it started. It's when you pull it out, it's the surface tension that pulls it back together, which seems a little bit odd, but we'll look a little bit more at that. So, I've got more pictures of this, but I think you believe there's surface tension. But my favorite thing is I'm skipping by all this stuff because I don't want to get any soap into this, because this is water that I just got out of the tap. I have no idea what kind of minerals are in it. But I put red food coloring in it, and I went down the I put red food coloring in it, well, so you could see it. Otherwise, it would be clear on clear. It would be harder to see it. So what I'm interested in doing, one of the experiments that Charles Boyes did, not alive anymore, is he had 2 drips running, and he had different liquids coming down the drips, so the drips would come down very slowly, and they'd get to the end, and they'd form, as much as they could hold before they dripped. And one of the 2, he had an alcohol drip and a water drip, and he had them with a shadow going against a wall. And he was having these 12 and 13-year-olds try to decide why is it that on the alcohol drip end that the drips were much smaller than the ones on the water end. Like the water would come down, and it would fill and fill and fill and fill, and that would finally fall. And the alcohol, it would fill to maybe half the size and then fall. And so the students decided there were a couple of options. One is that maybe the alcohol was heavier, and so maybe they had equal skins, so to speak, equal surface, but the alcohol might have been heavier. And the other option, or another option, might be the surface tension might be stronger on the water. So one of my favorite games, again, I don't know if this will work because I hope I didn't touch anything. If you put soap and stuff, it really lousens up surface tension. But I'm going to put water in this Petri dish. It's colored water. It's red water. And then we'll play a tug of war with the alcohol. This is alcohol in a vitamin bottle. So that your children get confused and take alcohol instead of their vitamins. So it's just rubbing alcohol. So the way the tug of war works is if you put some alcohol into the water, and if the alcohol, so what happens is there's all these molecules that are connecting to each other. That's how they get surface tension. If I put alcohol into the water and the alcohol has a stronger surface tension, it's going to pull itself together, and the water will pull itself away from the edges of the bowl. So you'll see a white strip along the outside. Is that making sense? But if the water is the stronger surface tension, then as I drop the alcohol in here, the water will pull away, and you'll see a blank spot in the middle, and the water will just pull up around the edges. Assuming this works. You understand the game? All right, tug of war, done without ropes. So let's see what happens. We're putting some alcohol in here. Oh. I love doing this because you can't see it, but the water's standing straight up. It's got a vertical edge. I am not kidding. If you want to walk up here and see it, it really is. If you keep doing this, the water will pull itself up. It's doing it right now. It's getting very upset. Anybody want to just come and look at it, Adam? So you'll go, oh my gosh. The water, it is standing up on the edge. Can you see the edge? It's just, it's vertical. It's starting to shake. You guys are moving, so it's going to break the surface tension soon. If I keep putting in alcohol, it'll just pull itself, and it'll start running its way over the edge. So, yeah, too bad you can't get a camera up here. But you can do this in your very own home. Just get water and some rubbing alcohol and drip away. The point of that is that the surface tension on the water is much stronger than the surface tension on the alcohol. In fact, the surface tension on water is so strong that we can't make bubbles with just water. In fact, you can't wash clothes with just water because the molecules are very closely tied together, so they won't go through the fabric. So now I can get rid of this. Had I put soap on here, it still doesn't want to let go. It's just fighting, and you can't see it, but it's like vibrating, trying to, you can't see it, it's going further and further away. All right, we'll let you see it. So now you have at least an intuitive sense that there's probably some surface tension, and you've probably seen, oh, I brought this for a document camera. Oh, wait, I got a picture of it. So, you know what water molecules look like, the Mickey Mouse molecule. They are, so it's a polar molecule, right? So they're very, very attracted to one another. And so when you're underneath the water, you've got molecules pulling from every direction. Sort of like if you had a big pile of magnets or something, the inside ones you can move around easier because they're all connected to one another. But if you went up to the surface, they're only connected above and below. They're not connected, they're connected surrounding them and below, but not from above. So it's pretty hard to pull them up. It's harder to pull them apart. You have to bust through the surface. When you add soap is interesting. Soap has this hydrocarbon chain. It's different. So it has this polar end, but then it has this non-polar stick that sticks up. And so what happens? That's pretty bad to say, isn't it? It's got this hydrocarbon chain on the end, and the hydrocarbon chain is what is hydrophobic, I guess. Hydrophilic would like, but it doesn't like water, so it goes up and points out. And that forces the part that's polar to squish in between the water molecules, and it gives some stretch to those molecules that are really trying to squeeze together, and that gives it some elasticity. So that when you put soap into water, the surface tension gets lessened, but there's still some surface tension. It's just a lot less than it was, which is why I didn't want it to get into that thing with the alcohol, because it would have just gone, okay, I'm fine. You take me, leave me. It's not as fussy anymore when it's got soap in there. Oh, I have that upside down, but you can't tell, can you? Can you even see that little writing? Huh, it was backwards. I mean, it doesn't really matter in terms of the molecules, but they're pretty symmetric. So adding soap will, I got more nice pictures. I forgot about this stuff. But here's a good picture. And exactly while you're looking at that, I should probably see. I added a bunch of glycerin to this soap because it's kind of has a little breeze in here. But I guess you could put a square. You have to also get the foam off the top because that breaks the surface tension too. Because all those little bubbles, they're not good. But if you, I don't know. I'm going to just try this just to even see if it's going to break. Okay, so it's going to be okay. Whoa. That's good. So even though that was square, it's still going to come out to be a spherical bubble, and that just has to do with calculus. So let's see what that has to do with calculus. No, it does. You don't believe me, do you? So we're going to see just how calculus has to do with this, and we'll see if we can make this happen. So you know what the isoparametric problem is in calculus? You probably just haven't heard it called that before. Iso, same, parametric. So it's perimeter. So if you have a fixed perimeter and you want to get the maximum area you can get in the plane, so you have a fixed perimeter and you want to maximize the area, what's the maximum area you're going to get? A circle usually. If you said square, then you've been doing too many farmer's fences in a farmer's field with rectangles. So if you want to maximize, so I want to make sure that this soap has not gone so far astray that it's not still trying to pull a tight surface. Like soap got added to the water, but I still think it'll give me a minimum surface. Meaning I think if I put this, if I were to put this thing in here, it's still giving me a flat surface. That's about as minimum as you can get, right? If it stuck out like that, I don't know if you can see it bouncing back and forth. Boy, it's really happy. I put in a lot of glycerin. If it stayed out in one of those positions, that would not be minimal. You probably believe that. So, but here we have a circle, and the minimum surface would be what you would expect, a circle. But inside that, I've tied a little loop, which I don't want you to think is, I don't know how to even show you that this loop, there's a little piece of thread here, there. Can you see that little loop? Everybody see that? So let's see what happens if we dip the whole thing in with the loop and see, oh man, I don't know if it'll happen. So the loop's looking pretty heavy. What I'm interested in is I just want to keep the soap everywhere, but I want to pop it inside that loop. And I'm going to try, but this is very happy soap, so it just might not let me pop it at all. Come on. Okay, I need several pencils. Glycerin is kind of like Valium for bubbles. And it popped. No, it didn't pop. All right, it's not going to have too much life left, so the whole thing just may pop pretty soon here. There you go. Do you notice when it popped, it immediately went into a circle. It maximized its area, which is significant because, see, there's like nothing there, right? I'm not like, boop, right? But out here, if I pop this, boom, it's not in a circle anymore. So we could do this all day with lots of different shapes, but what's significant about the loop when I pop that going out and maximizing its area is, what does that imply? You can do this. The what?
The water's cold.
Yeah, the soap film is minimizing its area. Is that reasonable? Okay, so even though I put soap in the water, it's still trying to minimize its area. We're going to use that to get back to that problem about the telephones. Remember we wanted to minimize the linear linkage? All right, so you wouldn't think this would connect, would you? But it does. So there's a problem called Steiner's problem, or in America, Steiner's problem, and I don't know how Richard Gardner would say it. Steiner's problem. I don't know. I can't do that. Jacob Steiner in the 1700s, actually he lived late 17th, so into the 1800s, I'm not sure exactly when he died. But he proposed this problem to determine the minimal linear linkage among a set of points in the plane. But he said he would permit you to add additional points, additional nodes in, as Adam had suggested. If there were 3 points, maybe we could put another one in here instead of just trying to connect around what's there. Does that sound like a reasonable? So he wanted to know, how do I minimize this? So another guy was the one that came up with this. Steiner did it pretty abstractly. So I'm going to start with the triangle if I can find it. I have an awful lot of that. There we go. And there we go. So it's hard to explain this, so it's better to show it to you. What I have here looks like the 3 points. And somehow I want to get bubbles to connect to the 3 points. But actually sideways I have a sandwich of 2 plates with just some little dowels cut. You can, it's just 1/8-inch dowel, just drill a hole and stick it in. It's not very hard. So you have 2 plates and 3 points. But the cross section, so I'm going to dip this into the soap film, and the soap film is going to actually create an area. It's going to connect around these 3 points, and then it's going to suck in and drain out, and when it's done draining, it will leave whatever film is going to be the minimal connection. You don't believe me, I can tell, but it will. So, and you don't want lots of other stuff going on in here. So, all right, we're dipping away. Come on in, the pizza's still warm probably. So I'm just draining this out, and I don't know if you can see what's happening, but it's draining, and we'll put it on a petri dish so we don't destroy anything. And so it's moving around, and it's gonna stop itself where there's going to be what's called a Steiner junction or a triple junction, and that triple junction just so happens to have 120-degree angles all around it. And you can perturb it. I don't mean perturb it like make it upset, but perturb mathematically. You try to push it, so you can do that. And it's moving very slowly, and that's what glycerin adds in more nonpolar pieces that makes the molecules connect, but they're much slower to react, and it keeps them wetter. It holds a layer in between it. So you could almost make it stick where it shouldn't, and it might just sit there for a while because it's taking forever to come back, but that would not actually be a stable situation. It's just going to take 3 years to do it, so I'm going to force it. So you might think to yourself, well, and it's not a bad thought, I've got 3 points, I've got 1 triple junction or 1 Steiner point, and I'm getting these 120-degree angles around them. So the next question should be, and it probably isn't going to be what you're going to say, but what do you think another question might be?
4 dowels?
4 dowels would be, but I want to stick with 3 for a while. So what's something I want to ask about 3?
Non-equilateral points.
Non-equilateral points, that's what I want to do, yeah. You never run to the next step till you've exhausted and figured out whether there's something going on here. So you have to think about the geometry. You don't have to, but I think you should think about the geometry. So let's think about the geometry. I might not even need this other one. I'll just keep doing that one. So if you think about it, if it's true that any linear linkage always has 120 degree angles, that doesn't really make sense because I could have 3 points like this, so I'm not going to get 120 degrees. That's not going to be minimal, so that doesn't make any sense at all. So 120 degrees and when? So let's go to triangles because that's not a, well, all right, it's a degenerate triangle, but it's not a very nice one. So we have an equilateral triangle that looks pretty 120 degrees. What if we make a triangle that looks more like this? A right triangle, for example. Is it possible that I could get some sort of interior point where I could still get 120 degrees? And if so, if this is A, B, C, where should that triple junction fall? Closer to the A, closer to the B, or closer to the C? This is geometry. Closest to the, how many for A? How many for B? How many for C? How many for not in the figure and it won't even connect that way? How many don't know? Oh, you don't know. Thank you, honest people. All right. So a lot of you picked C. Why? I'm assuming this is 90. These are not 90, right? Okay, 90 is the biggest angle. Why should the triple junction, if there is one, get closer to the 90-degree angle? Just because. Okay, think
It
about
seems
it.
to make sense visually, because if you, I don't know,
If you start at some point on the triangle and you
Uh-huh.
think about pulling it in
Yep.
any direction, thinking
Yep.
about how the angles change.
Okay, so it is a matter of dynamics. So if I take a point here, how to explain this? As I pull a point back further and further and further, the angle gets smaller. Or if I push it out further, the angle gets bigger. This angle is bigger than this angle is bigger than this angle. I don't know if you believe that. I guess you could just take 2 points and hint me that I should have done that. If you take, I don't know, 2 points, and you look at this angle versus this angle versus this angle versus this angle, is it clear that the angle's getting smaller? Okay, so if I want to get 120 degrees, I'm going to have less to move from here. I'm going to have to move a lot further from here to get 120 degrees. I mean, because this is like 30 or something, right? I'm going to have to push it way back in here. So I might as well start at the biggest angle. Yeah?
It kind of makes more sense to me to think of it as minimizing travel time. Which is obviously like you want to, you know, you want the same path to the faraway one to be, okay, I don't have the words really to describe it.
Well, I actually thought I knew what you were saying, but now I don't.
Okay, just
Okay, so I think I know what you're saying. So if I put it here, I'd have lots more travel.
Yeah, or just in the case of like a sausage where it's really tall in one direction, you want to like only travel across that long path like once instead of twice.
So where do you think it would land in this?
I mean,
Closer
closer to
to
the
the
short
bottom.
base.
Closer to the, yeah.
Yeah, right.
Good, no, that's very good. That is very good. Did you all understand what he was saying? All right, so let's see what happens. We have lots of triangles. We're never gonna finish anything. I got way too much. All right, so we've got this, this is a more or less 90 degrees, which is as good as I could drill it. There you have it. And you can try, where's my perturber? My perturber, otherwise known as a straw. So you can move it down, but it's gonna come back. But it gets more interesting. So let's look at a more obtuse angle. So this is a right, supposedly a right triangle. I've got one that's not a right triangle. Any idea what's gonna happen on that one?
Center should be more or less the center of the square.
Should be where?
More or less the center of the triangle.
Center of the triangle?
Which center? Which center is a really great question.
I don't know. Do you have any idea what the largest angle in that one is, if you had to roughly approximate?
the top one.
How much shall we think the angle is? 160?
145.
Turns out it's 120 degrees. more thinking about how are you going to pull in from a 120 degree to make it a 120 degree. That's what I want to know. You might not, that's right. In fact, anywhere from 120 degrees and up, you don't get a triple junction. It's redundant. You get a degenerate triple junction. It went right back to the 120 degree. You can perturb it, but it's going to keep, well, if it's not too glycerin. So you can force it, but that one actually is pretty quick to move back. 120 to 180, it's just going to move back because that 120 degrees is stable. And if you've studied chemistry, you know a lot about those angles. All right, so I want to do a lot more. So, well, let's go to 4s. I have a lot of 3s that also have lakes in them and things, because it's interesting what happens when they have a surface that they have to go around. I better show you one of those. Those are pretty fun. So that's a lake. And it's not quite an equilateral triangle. It's almost more, as you were saying, almost isosceles. It's interesting. You should realize that the reason these problems aren't solved is because there aren't unique solutions. Well, that's not true. There is one minimum solution, but there are often many stable situations for this. So there's lots of local optimal points. So let's do one lake just for fun. Oh, this one is attached to my finger. Hey, get it off me, you. And I have to pop the lake. Oh, come on, lake. There we go. Okay. Oh, goodness. All right, here's the lake. Except I probably can get rid of one of those sides. It depends on which side you want to pop. So right now it's connecting everybody. So you just have to decide who looks the longest. This guy? Get rid of that. There. So you're going to have a minimum depending on which one you want to get rid of. And you just pick whichever is the shortest side. And you're still going to end up with 120 degrees. It'll just be tangential to whatever you're going after, unless the surface goes out beyond. I've got a whole bunch of those too, but I'll let you keep some questions in your head. So if I make this lake go outside, are you following what I'm saying? That gets interesting too, but it still works. All right, let's go to 4. We'll start out with a square because we started out with an equilateral triangle. Where's my square? Oh, wait, I didn't show you something cool. Where's my moving point? I forgot. So yeah, you can show what I just showed you with a moving point, and you can have basically dynamic. Are you following what I'm saying? Except for, oh man, this hasn't been done in a long time. I'm gonna get some soap on there to see what I can destroy. Oops, my finger's in the mix again. Stop that. All right. I think we'll just do this and get stuff wet. Uh-oh, that might not have been a good idea. So let's see. You wanted to go home sometime tonight, didn't you? So obviously, with 2 points, it's just gonna connect them, right? And then as you oops, it pulled apart really fast. So you see where I'm at about 120 degrees as soon as I, oops, not anymore. So there's my equilateral triangle, and then as I move it around, can you see how am I in your light, in your way? Can you see how the triple junction's gonna just keep following? There's your equilateral, or your isosceles that you were talking about, and so on. I've always liked dynamical. I think that's so fun. Yeah, all right, got the drift on that? Okay, good, let's go to, oh, it's stuck. Oh. Okay, this is why I did not use the document. I knew these overhead projectors would come in handy someday. Let's not throw them away. We have to dig a while. All right, 4s. All right, what's going to happen with 4? So minimal, could it be, you could connect everybody going around and assume the sides are 1 with path of 4. Or you could connect 3 sides and get a path of 3. Other options. Diagonal? Or
Yeah, the
diagonals are somebody say
intersection
that.
of the diagonal.
Intersection, okay, so that would be 1 by what? Root 2, what's 2 root 2? 2.8-ish, that's less than 3. Other thoughts? Think about electron movement. Think about Fermi. You'll recognize this if you've done physics and you've looked at electrons, because I spent a long time at Fermi lab in the summers for about 6 years running watching particle collisions. And it looks just like this. This soap really is happy. Okay, stop it. Whoa! Sorry. It's doing funny things. Oh, that's not that funny. Oh, yeah. All right. Wow! It's got 2 triple junctions. You've seen that where the electron goes. No, you haven't seen it.
Yeah, it's
Go
like,
take some
it's
physics.
like a fine effect.
A fine, yeah, right. And then Fermi lab, they just do collisions all day long, so you're just pulling out, just trying to get neutrino. All right, so here you have it, and you could make one. Oops, nope, you can't. And it turns out, well, after that centers itself, that will be the identical minimal linkage as the other one, because I got a square. But if it's not a square, one of those is local and the other one's maximal, or what's it called? Global, I guess. Yeah, yeah, so right now they're the same, no matter, it doesn't matter if it's that way, that way. Okay, so let's take another 4-pointer. We don't want to go up to 6. Oh my gosh, the time is just flying here. This is kind of how 304 went today. Some of you are in my 304. It's like I looked at the clock and it was over. And some days I scream. It's like just magic, it ended. Okay, 4s. Here's a 4. I know, I scared the class too. Ooh, there's 4. I pulled everything in a little bit. See any 120 or bigger angles? I think we're going to get one degenerate triple junction and then another one on its own is what I'm thinking. Honestly, I don't remember, but I think so. I think this guy's going to hook up. And I think this one's going to pull in. But why should I tell you? Just let the bubbles. This is what Charles Boyce would say. He'd say, ask nature, it'll answer if you ask it right. This one actually, this is just about willing to go into 2 triple junctions, so maybe that's not 120. Except it slowly seems to be sliding. Oh, it's pretty happy. So it's not quite out there. So I think this might just be a tad less than 120. I'm sure I could perturb it and it would stay there because it's so close, but real bubbles wouldn't. I mean, theoretical bubbles would not, but these are very wobbly bubbles. And you could, yeah, so if I got this, I actually worked this out. Oh man, I got so everything up here. I worked this out, but I can't remember. I guess I should be able to figure it out. But I don't remember what, lengths I put in. So I can't tell you, but okay, so let's see, which one should be minimal? That one? Oh, the other one is minimal. This has got way more diagonal. Look. That one's gonna be the minimal. I don't know if we can, but it's true. All right, let's go to one that looks like this. What's gonna happen there? So we're still getting 2 triple junctions on the 4s. I think these are cut, so these are 120s up at the top. So that was the intent. We just need to drill in some, I went to St. John's Glass, and I got a sheet of this plexiglass for like $7, and I bought the dowels for 25 cents. It wasn't a real expensive project. So, whoa. This is the happiest soap I have ever seen, and I've never seen it do this. And it is stable. Oh my gosh. Those are 120s. That just shows you how you can get a local minimum that makes no sense at all. Because if we try to go horizontal, even if I go from this end, I think it should work its way back up and go. It just might take a while. I'm pretty sure I cut those pretty darn close to 120s. So there should be 2 degenerate, there we go, boom. So that's interesting. Seem to do that. That's pretty cool. All right, so enough on, yeah. So I guess we can go to 5s. You know what the angles are in a regular pentagon? You can do this. What are the angles in a regular hexagon? 60? I don't think so.
120.
120. Pentagon has bigger angles or smaller angles?
120.
Bigger, smaller? Bigger, smaller. How many for bigger? How many for smaller? How many for I don't know? Okay, so back in middle school. You forgot everything. If you take a figure like I guess that's a hexagon. All right. So you usually cut it into triangles. So there's 1, 2, 3, 4 triangles of 360 apiece. I don't know how much 4 times 360 is, but then, well, 4 times 360 and then divide that by the 6 angles, so that's 2/3 of that, right? So 3, 182, so I guess they're 120 each or something. No, I can't divide. Oh, what did I do? I don't know. I took 4 triangles times 180, oh, that's the problem, I made them all. Okay, 4, and then we're dividing by 6, 2/3 of 180, that's 120, sorry. So if you take a pentagon, damn, man, this thing. So then you're gonna get 3 triangles, I think I can do this, 180, and then you're gonna divide it by 5, but I don't know what 5 is, goes in there, but you can tell me.
108 is 100.
108. I know it's less than 120, whatever it is. 108? I'll take your word for it. So if it's 108, where's my pentagon? Oh, I don't know. Pentagon yet?
It's on the.
Oh, it's on there, but I forgot to show you this one. This one's very neat. I really need to show you this one. Because I made this at a particular ratio so that something interesting happens. And you'll just have to see to believe you. I also have one with a moving 2-point, but we don't have time. All right, this one is really cool because normally you can perturb these to make a global or a local minimum, right? You can, and this is the global. The local would look like this. Except for it's not gonna, this is very cool. It's gonna come down and it's gonna go boing! Boing! Okay, there's a field called catastrophe theory. That is a catastrophe point. Y'all likely look that up on your own. It simply will not do that. And the reason, I forgot the ratio. I think this is 1 to the square root of 3. Square root of 3, so it ends up with a 120 angle going this way. I see 1 by the square root of 3, 2. Yeah, I made it square root of 3, well, close, 1.8 or something. So, yeah, so it won't connect this way. That's one of my favorite, that's just the most visual catastrophe point I've ever seen. It just, bing! Oh, that's just awesome. All right, back to the, where did I put the pentagon? I threw it over here somewhere.
It's right under your left hand.
Oh, it is, thank you. All right, so if they are 108 degrees, I think that's what you just told me. What do you expect for Steiner points? How many do you expect? I haven't really been seeking patterns here, but I guess I should. With 3 points, we got at most how many Steiner points? 1, and with 4 points, we got at most how many Steiner points? 2. 5 points, you'd expect at most 3, and this one gives you 3 because each of these are trying to pull in to get the 120 because they're at 180, so they have to yank themselves in, right? So you can perturb this. It'll still give you the same picture. It'll just be symmetric, right? So if it'll just boing to the other 3 sides. Are you following me? There is, for a regular pentagon, there is one stable configuration. That's it. I mean, that's it, or that's it, or that's it. Right? Same thing. Honestly, if you look at the architecture guide where this comes from, he shows 5 different ones. They're all. I just like turn the book, but he spends 5 pages with each of them being different. That's Peter Stevens, who's one of my favorites. But I thought, why did you do that, Peter? So how about the hexagon? So now you know about the hexagon. It has how many degrees to an angle if it's a regular?
420.
Yeah. So how many triple junctions would you expect at most? 4 at most, and how many at least? Maybe 0 at least. Here's a 0. There are 3 different stable configurations in hexagon. They take a while to get, so I don't know if I can do this. But that's actually the most minimal. That's your global minimal because you have the 120. Boy, I haven't done this in too many years. I still got a lot of hot air though. Okay, no. Okay, now I'm getting there. All right, there's one of the stable configurations. So it's basically making a honeycomb pattern from the interior. Well, there's others. I don't know if I can get to them all. No. Yeah, there's another I got this. I mean, it's easy to figure out the geometry. They go in order. You know, there's an increasing order. The hexagon is the minimalist, the most minimal, and then there's those other configurations which I can't remember. So what I wanted to show you, and there's never enough time. I have all these little notes, but you know how that goes. I just kind of skip them all. I wanted to show you Bernoulli's problem, the Burke-Easterholm problem, because it's really interesting. And I guess I'll go back to the board and have this thing hit me in the head again. I don't really need this. There, go there. So a famous, pretty famous problem anymore, anyway, several of them. If you had a river, and you have a town here, or I don't know, so the person here, A, and a person, or a place. Here's the barn or something, barn with an A, and here's the house with a C, and the person has to walk to the river and get a bucket of water and then walk to the house, or one of those stories. And we don't even need this, because sorry I made no one wiped this all off and I'm not using it. So if you want to figure out where does the person go, if they're walking at a constant rate all the time, where do they, do they go this way if you want to minimize their time? Yeah?
Make an ellipse with those that both look at, and then when the ellipse intercepts the standing to the river.
You could do that. There's a much easier.
I
I think
believe
you're taking
walking
multivariable calculus, aren't you? Yeah.
So I believe I go directly to the stream.
I can't hear you.
I said walking near streams is more pleasant, so I maximize
Oh,
happiness
go
over
back
time.
to sleep here. How about you reflect C over here? So here's C and here's C prime. So I want to travel the right, yeah, so then I'll just go like that. And so I need to have, I'm going to hit right here at B because this distance should equal that distance. Fair enough, but it's true, you can draw ellipses. But I just want to go from A to B and B to C, and I know the straight line is going to do it for me. Fair enough? Okay, so the tricky part comes if I say now life is different. I still want to minimize the time, but the person it can walk twice as fast from here as he can from there, because by the time they pick up the bucket, it's heavier, slowing them down. So that changes things when you start messing with rates, and now we're getting towards some of these Fermat optical problems, which I love. So it's not going to be the same place, because they can walk faster here. So is B going to be up higher? I know it would be higher. And up higher or down lower? Higher. So they're going to travel longer here because it's going to take them they're going to longer distance here because they'll take them a longer time here. Is that reasonable? So my claim is that the soap bubbles will not only solve this, but they'll solve a more incredible problem. So the way I'm going to use soap film is in order to make the difference of taking they go twice as fast on this, is I've got some plates where I put a step in them. So the river, or whatever it is along here. That's this horizontal piece. I guess I can make it like it was sitting over there, right? And this is to get to C, but it's really over here, but I put it over there because same distance, right? So, or I guess it probably goes this way, because here's where the person's going twice as fast. The reason I know they're going